In the drawing, you pull. In the extrusion, you push. You see my point? And there is a material which accumulates here, and this is known as the dead zone. And maximum shear stress happens at 45 degree. Therefore, it is 45 degree dead zone, and angle is this one. This angle is 45 degrees. Is 45, 45, 90 degree. So this is the dead zone. And in the forging, you see in the forging, if it is a closed die forging, suppose if you have a forging, this this forging press goes down, and the in the final shape, this is known as the I would say this is the piece out of the forging. So this is extra piece. What we call this piece as the flash, and the flash is known as the waste. You have to waste by cutting it off from the forging piece in the forging case. But in the but in this case, the this is coming out of the die. We call this in extrusion. The flash is not waste but the part. You see my point? And the billet, this billet, at the end it is left, it is waste. These are just terminologies. I'm going to show you one slide that will help you to understand the forging. This is the forging equipment. You see the forging, the piece is coming out of the forging die. This is the piece. He's heating up this piece to release some strain hardening so that it will not crack when this is sudden uh, change in the temperature. Okay, now we want to treat the material during the process extrusion. You see this big piece on the conveyor belt. These are the rollers and this big piece. Have you seen some uh, Home Depot, some flashing, aluminum flashing for our roofing, gutters, some other things? These are all extrusion. These gutters are also extruded material, extrusion process. Some shapes, cross sections, I would say these are the cross section, how it looks like. Some cross section have, yes, the drawing process. Yeah.
I mean, I know one's pull versus push, but is there certain metals that you only do one of them with, or certain applications you should only do it with?
It depends upon the, I think the length as well. Certain time, maybe which one is easier and cheaper. These are the different. This is in this characteristic forging. The slug itself is forging piece, which is our required piece, and the extrusion flash, which comes out of the die, is known as the part. Waste is inside the die, which we don't need. You see, there are different types of extrusion processes. Direct extrusion, you see, the ram is the ram is pushing the material. This is known as the direct extrusion. This is indirect. Look at here. These are the dyes, okay? This is the dye, color dye, okay? And now you are pushing the dye inside. The material is come out. It's coming out from the same piece. So it's like a small um, billet which is to be extruded. And now you need to have a tubular type of actually you have a tube and you are pushing it. This tube it generates like a hollow tube, hydrostatic. It is not in direct contact with the forging, but it's some liquid inside. Cold impact. I think the kitchen utensils like a pan or something like cooker extrude it. So might be as Arden asked me, what how would you when would you use extrusion versus drawing? So I think for extrusion for the drawing you may have to have a longer continuous piece. In extrusion you might have a smaller piece like a pressure cooker if you want to extrude it, like in this case extruded tube. Have you understood the indirect process? This is my indirect extrusion. The material comes on the same side of the die, the ram. Here is the direct extrusion. Flow types, laminar flow, turbulent flow, redundant work can bring outside the billet in the center. Okay. Steel extrusion. What are the requirements to extrude the steel? That the processing temperature should be around 2100 to 2400 Fahrenheit. Melting point for steel is 2500 Fahrenheit. The die temperature is 400 Fahrenheit. It is hot above recrystallization point. Lubricant, a glass, viscous lube, molybdenum, graphite. These are the lubricants. Okay, let's do some analysis. Which formula are you going to use? External friction, internal friction. You see, there are two frictions internally, externally contact with, of the workpiece with the die is external contact. External friction, internal friction, this is internal because they are both the same material which is shearing, flowing. Material is flowing at 45-degree. Okay, you see my point? Some assumptions that no redundant work means like energy is not turbulences. No redundant work can use the slab analysis. Dead zone sets up at 45 degrees. These are some assumptions. Okay, upper bound analysis. I'm going to jump over to the final formula. Work input by the external force is equal to the plastic work expended. So the power pressure equals to the internal friction plus plastic work plus external friction. So you see, try to understand this pressure is on the left hand side. It is overcoming the internal friction, which is over here, internal friction, external friction, and plastic work to compress it. So three types. And now we will find out the formula of these three types. And also work rate equals to power. We know that rate of work is power, and work rate equals area times stress times velocity. Pressure work input. On the left hand side, you are putting pressure, and this is W dot P. Please write down this work. W dot P equals to pi D1 square. D1 is in the back side, a bigger diameter. If I ask you one thing, let me show you one thing. Okay, how did you calculate the reduction area here? You remember that reduction area? And then the next rate of work is internal friction. This is just a derivation. We will jump to the formulation. Volume flow rate. Please write down this formula. Volume metric flow rate, area 1 times the velocity of the ram equals to area initial velocity. Let me go back to this picture. This picture here. Some volumetric flow, you can find out the instantaneous velocity of the material. Frictional work input can be found using this formula. The plastic work to compress the input. When we equate these three rate of work, you get this formula. So you need this formula and this formula, right? This formula you need. P is the back pressure. To tau flow, you already know this is the more stress circle required to let the material flow. D1 is the initial diameter, D2 is the final diameter. Extrusion ratio, RE. Please write down this formula for extrusion ratio. Now, can you relate this? Can you relate this formula in rather than d1 over d2? Can you write down RE? So let me show you the next slide. If you plug in RE, RE equals to d1 over d2 whole square, right? So if you replace this, if you do the math, look over here, can I write down like this? 1.707, like divide by 2, multiply by 2, agreed? Divide by, multiply by, this 2 goes in the power. When this goes to the power, so ln RE, so you're left with ln RE. You understand what I'm doing here? So it can also be written in this form as well as in this form. So that's the what the next slide is. The billet and wall friction. Friction stress equals to the shear flow stress. Due to the billet and wall friction, change in pressure times the area equals to torque flow. So this is also some explanation. So let me write it down here. The final answer for this one for the average, right? This one, final answer. This is for direct extrusion. What if you have indirect extrusion? So let me show you. In indirect extrusion, the figure looks like this. The die comes and it pushes the material and the material flows towards the die. And the last slide, I'm going to show you the formula for this one. Yeah, over here, this is indirect. I want to come to the conclusion of similar ratio. Pressure over 2 torque flow for the indirect extrusion. So you should be able to solve this problem at home for the test. Yes, for indirect extrusion, this is the formula. For the direct extrusion, the formula is a little different. In direct extrusion, the formula is a little different. And you know, for more stress circle, for the cold forging or cold drawing or cold extrusion, this is the formula. And for the hot, the formula is changed. This is the formula. Strain rate, and strain rate is this formula, where epsilon rate is given by this. The remaining portion is not that necessary. So we will solve this problem next time. And let me ask you, do you want me to include this